Hello, hello, hello. Hopefully everyone can hear me. Hopefully. Let me know. Hello to everybody who's been waiting. Apologies for the slow start. It took a while for things to get changed over. We've just had a live physics class, so apologies if you've been waiting for a while. But welcome everybody. Welcome to our SnapRevise A-Level Chemistry Sunday session. Today we're looking at practical techniques in organic chemistry, which is the second of two sessions that we have on practical techniques. So we're going to be looking at some of the practical techniques that you need to know for organic chemistry. But please feel free to say hello in the chat. Those of you that are here as newbies, welcome, welcome. And if you are an oldie back again, hello and welcome back. Really nice to see some familiar names in the chat. So hello, hello. Can everybody see my screen okay? And can everyone hear me okay? I just want to check that everything's working all right. Oh, thanks, Rosh. Okay, brilliant. It's on my list, but I'm probably not going to pay for it, so I'll probably wait. But hello, how are you doing? Hopefully you're nice and chilled now. Hi, yeah, lovely. I'm good. Thank you, everybody, for letting me know that everything is working all right. We'll get started in a second. So hello again to everybody. So I'm Alyssa. I'm one of the tutors in SnapRevise. This is our A-Level Chemistry Sunday session. So let's have a look through. So first of all, I'm just going to introduce myself. If I move my laptop so I can see it properly. Oh, there we go. Finally, it woke up. So my name's Alyssa. I'm one of the chemistry tutors on SnapRevise. I have a PGCE in chemistry education from Oxford University, and I've been teaching A-Level chemistry for the last 6 years, and GCSE and Key Stage 3 as well. So really enjoy teaching science. I think science is such a cool subject. So really awesome if you guys have chosen one of the sciences. Obviously, chemistry is the best in my opinion, but they're all pretty good. Thank you, Rosh. Yeah, you too. Hope you have a great day as well. I'll see you soon. Okay, so I'll pop this on at the end of the session as well. But if you are interested in just trying our tutoring package, then please feel free to, because we have a free trial for 7 days of tutoring for free for 7 days. So if you use the code tutor trial 7. When you check out, it will give you 7 days for free. You can try it, just check if it's the kind of thing that you might like. We've still got sessions going on over the summer holidays. So if you're wanting to keep on top of your revision through the summer, then it might be a great opportunity for you to just try it out. And then obviously the sessions will continue into the new year, into the new school year as well. So if you fancy that, then please do have a look. It's tutor trial 7, and we've popped the discount code in the chat as well. So for this session then, what we're hoping to do is recall and apply knowledge of separating funnels. So what are they? How are they useful? How can we use them? We're going to look at recalling the different types of filtration. So how you can filter something, and the 2 different types you need to be aware of at A-Level. And we're going to recall and apply knowledge of recrystallization. So what's needed for that? What's the point of it? What are they going to be looking for in an exam, etc. What we're not going to look at, though, is thin layer chromatography, because that's covered in a different web class. Hello, hello, hello to everybody who's saying hello as well. Brilliant. Fantastic. Nice to see people from all over the place. That's awesome. That's very cool. Okay, so if you are following one of the 3 main exam boards in the UK, AQA, OCR or Edexcel, then we have the specification points that we're going to be covering in the front of our PDFs. If you haven't got a copy of the slides that I'm going through now, they are available in the description of our YouTube video. So please download them, because you can keep them. You can use them for revision later on. You can come back and rewatch the web class and go through it again. It's really useful. So they are available to you. So please feel free to download them. Is this AS or A-Level? So it's actually going to it's covering the whole of the A-Level. So it's including AS content as well, just so that you're aware. It is both. So technically we could call this A-Level. But there is some AS content in here. Yeah. So as I just said, it is both, yeah, year 13 and year 12. Okay. Hopefully that's useful. So this is that was the AQA specification points we were covering. This is the OCR specification points that we're covering. And then these are the Edexcel specification points we're covering. So like I say, if you are interested in downloading them, then please do. They're in our in the link below, and they can you can download them, reuse them, use them for revision, use them now, print them off, whatever you would like. Absolute pleasure. Okay, so part 1 then, separating funnels. Let's have a look at what separating funnels are and what are the point of them. So what's the purpose of a separating funnel? Sounds like a silly question, but it's not. Why might we choose to use a separating funnel? What's the, in a laboratory, when might you need to use a separating funnel? Anybody want to let me know in the chat what you're thinking? To separate the organic layer from the water layer. Brilliant, well done, fantastic, exactly right. It is, we use separating funnels to separate an organic layer from an aqueous layer. Fabulous. So this is to, oops, I'm drawing on it with my hand. To separate an organic layer from an aqueous layer. So one that is dissolved perhaps in an organic solvent from one that is dissolved from some substances that are dissolved in water. Fabulous. And while we're here, let's just double check which is going to be more polar. Which compounds are going to be more polar, the ones in the organic layer or the ones in the aqueous layer? Which are going to be more polar? So which solvents are polar, aqueous or organic? It is aqueous. Well done. Oh yeah, that's a nice thought as well. To separate two immiscible liquids is lovely. Yeah, that's a very good phrase. Yeah, I can't see any reason why. I think that would work. Separate immiscible liquids. Yeah, that's good. Yeah, well done, guys. It is the aqueous layer. Fantastic. Is our more polar. And our organic layer would be less polar. Fabulous. Okay, so we've got our separating funnel. We've got 2 layers in it. How? So we need to pour our reaction mixture, which should contain 2 layers, into a separating funnel. Oops, can't spell funnel. Double N. Please do let me know if at any point you can't read my handwriting, because I appreciate that, you know, it's not the best writing onto this this tablet. So please do let me know if you can't read anything or you want me to rephrase something. So we're going to pour the reaction mixture into a separating funnel, and then we usually invert it just to kind of mix them. Oops, or if I press a button, there we go, and invert just to mix them. Separating, I've spelled wrong as well. Yeah, lovely, good, Zara, fantastic, really good. Also, this live is going to be less than an hour because I'll need to finish just before 5 o'clock. So it won't be quite an hour. Hopefully that's useful, but we'll probably finish about 5:02, I would guess. That's what we're aiming for anyway. Okay, yeah, so great question. Why is it aqueous? And Zara has answered that question brilliantly. Aqueous means it's dissolved in water, so aqua meaning water. So aqueous is something that's dissolved in water. And water is a very polar substance, very polar solvent, so it dissolves polar molecules. Polar dissolves polar because they can interact well. Nice, great questions. Okay, so once we've inverted it, we'll probably see kind of like a bubbling effect. So we have to make sure we let our layers settle. Now, how on earth, and one of the biggest challenges that I found when I went into the lab, is how on earth do you work out which layer is which? Anybody got any ideas how we know which layer is which? We need to identify our layers, but how do we do that? Lovely. Okay, SG said densities. Brilliant. We can definitely look at densities. How is that going to help us? What bits of information do we need to know? Okay, good. The more dense layer is going to be on the bottom. The less dense layer is going to be floating on top. Fabulous. Okay, now usually organic is a heavy layer. That is very true. So usually organic sits on the top, and as you drip water, and then you can run off the bottom, the aqueous layer. But it's not always, so it's good to check. And anybody know what check or how we can do a quick check? So let's say that we think our organic is on the top and our aqueous is on the bottom. How do we do a quick check? Anybody know how we could do a quick check? Yeah, brilliant. Well done, Vincent. Exactly right. That's fabulous. So if we add a little bit, it's usually easier just to add a bit of water, just add a quick squirt of distilled water into the top of the separating funnel. It will flow down the side and you can just see which layer increases in size. Whichever layer the water has joined must be your aqueous layer. So you can just do a quick double check if you're not 100% sure. Or you can add some of the organic, exactly, or some of your organic solvent and see which one that sits in as well. Brilliant. So that's fantastic. So 2 different ways that we can identify which layer is which. So we've got our the lower density layer will sit on top. But whichever that one is, we're not sure, but we can check by adding some more of one solvent and see which layer increases. Identify which layer increases. And that's super, super helpful when you're actually in the lab to be able to do that, to just double check. I think it's this one. I'm just going to check. Yes, that's the water layer. That's the aqueous layer because that's the one that's increased when I've added water. Fabulous. So then you can need to decide which one you want. Do you want your aqueous layer or do you want your organic layer? So if you want your aqueous layer, then you're going to need to run as much of the liquid off as you can. You get down to, so there's a tiny amount maybe of your aqueous layer left. You might want to add a little bit more water just to increase the aqueous layer again. Run off as much as you can, add a little bit more water. You might want to invert it a couple of times perhaps, just to try and make sure you've got all of the aqueous substances out and run it off. And eventually you will have collected all of your aqueous content, all of your aqueous solution. Or if you want the organic, then you're going to need to do it in the other way. You're going to need to run off as much aqueous as possible. Try and get it as close to completely as you can. You might want to add a little bit of your what's it called? Add a little bit of the organic layer to your waste basket just to make sure that you've gotten rid of all your aqueous layer. I guess it depends which reaction you're doing and which is more important to you, having no water in there or having all of your aqueous or all of your organic content. So very useful. And we do a lot of organic reactions, a lot of organic mechanisms when you get into the laboratory. So it is very, very useful to be able to separate these two using a separating funnel. Okay, so if you keep track of volumes used, then you can see that that's true. That's very true as well. Yeah, good point. I mean, you might be producing an organic liquid in your reaction. So the amount of liquid that you've got might depend on kind of the percentage yield of your reaction. So, but if you know that, you've got a huge excess of water, perhaps, compared to your organic, then that might be obvious then. That's very true. So yeah, that's also a nice idea. Mohammed says, is this AS? So sort of, you might have used this in AS, but some of what we'll be going through will be AS content. Some of it will be A level. One quick question. Why is it that iodine is purple and black, but then also brown on mark schemes? Oh, great question. Because it depends who you ask as to what color they want it to be identified as. It's an awkward one. There's a couple of things in the exam boards where they disagree on what you need to call it. The relative mass of an electron, for example, which is a fundamental particle, but they still can't decide which they want to be used, which is the correct number. So I think it's literally just whichever exam board it is has decided that that's the one they want to use. So you just have to unfortunately learn which your exam board is looking for. Sorry about that. Iodine and English. Oh, I see. Yes, good. Okay, so what have I put? Oh, run through and collect desired layer. I never put that in. Whoops. Desired. Whoops. Why can't I spell desired? Desired layer. Lovely. Yeah, see how, so Nabil, you said 1/1870. Lots of people say 1/836 or 1/835 or 1/2000. I mean, they changed their mind. Georgia, so like I say, you might have covered this in AS, but practical content is often kind of focused on maybe a bit more in A2. It depends when you've done your practicals, really, because actually when you use a separating funnel, you probably are more likely to come across it in A2, but in terms of the content, it's not that difficult. So probably more likely A2. Yeah, exactly. Or you can say negligible mass, which is not so useful. Okay, so let's have a quick go at this question. I've realized I've talked a bit too much because I like doing that apparently. An experiment to prepare a sample of 2-chloro-2-methyl-propane uses the reaction of 2-methyl-propan-2-ol with concentrated hydrochloric acid. Steps of the experimental procedure are as followed. Blah, 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 blah. Separate, I'm going to highlight that one, separate the 2-chloro-methylpropane from the aqueous solution using a separating funnel, etc. Draw a diagram of a separating funnel that could be used in step 3 and then label the 2-chloro-2-methylpropane layer. Okay, no, I'm sure you haven't been doing much practicals, Georgia. I can totally understand that because it's, not been a particularly good year for practical use, has it? Unfortunately, which is such a shame for you guys. What exam board is this? I'm not 100% sure, actually. I would guess OCR probably, but I'm not 100%. So it's draw a diagram of separating funnel. So we need to kind of get this nice bulb shape in order to show that it's a separating funnel. We want some sort of tap on the bottom. We need some sort of tap. And we're going to need 2 layers, and we just need to work out which one is which. Oh, Vincent says this is an AQA question. There we go. You reckon? I mean, it looks pretty similar to most of the exam board style questions. So, oh, that's very specific. That's impressive knowledge there, Vincent. That's impressive. Vincent reckons 2018, so feel free to go and double check, but nice if so. So what are we looking for then, guys? What we're looking for, we're labeling the 2-chloro-2-methylpropane layer. So we've put 0.2 moles of 2-methylpropan-2-ol and 70 centimeters cubed of concentrated hydrochloric acid in a large conical flask. Stopper and shake the flask at intervals, releasing any pressure after shaking. Separate the 2-chloro-2-methylpropane from the aqueous solution using a separating funnel. So we've got 2-methylpropan-2-ol. Here's some nice data for us. And we've got 2-chloro-2-methylpropane. So which layer is which? These guys are saying 2-chloro-2-methyl at the bottom. Why? We reckon this bottom layer is our 2-chloro-2-methylpropane. It's more dense. Fabulous. Good. So we've looked at our density data, which they were given which they gave us in the question, and the density data says the 2-chloride 2-methylpropane is more dense, therefore it has to be the one on the bottom layer, and so our 2-methylpropan 2-ol will be the top layer. We might also, I have just realized I didn't draw a stopper, so we might also want to draw a stopper on our flask. Ah, brilliant. Thank you so much. That's really great to hear. Lordina, thank you. So these, you know, this is why we do it, because we want to try and help as many people as we can. Unfortunately, it's not, you know, we can't afford to do it all day, every day. Otherwise we would, I promise you. But really good to hear that they are useful. And that's thank you so much for saying that as well, that you direct all your students to this channel. It's, I mean, we try our best. We do try our best. Okay, lovely. Right, so I think that's everything. So you'd get 1 mark for your picture of your separating funnel, and then 1 mark for labeling the correct layer there. Okay, feel free to ask any questions as you do in the chat, and we will keep going. So part 2, we're going to look at filtration and recrystallization, which they tie in quite nicely together with each other, which is why we like to do them together. So we're looking at filtration and recrystallization. So first of all, we're going to look at filtration, the 2 different types of filtration that we need to be aware of at A-level chemistry. Hopefully everybody's had a go at doing some type of filtration, even if they did it at GCSE or even Key Stage 3. You might not have done this right-hand setup, but we'll go through what that is, what that means, and how it's different in a second. Oh, have I missed a question? Sorry. Is this A-level content for OCR? So I think it will be separating funnel. I'm sure a separating funnel is AS content because it's really not that difficult. However, I think the first practical in which you definitely use it is an A2 practical. So it depends whether or not you are lucky enough to have tried, like on an A2 assessed practical type thing. So it's whether or not you've been lucky enough to try other practicals which have called for a separating funnel but aren't necessary for the AS. So Zara says they did it in AS. Khadija, apologies if I said your name wrong, said they think it's AS as well. So I think you guys, you hopefully would have covered it in AS. So what's the point of a filtration? Why do we filter something? Oh, okay, so Zara says you used it when you did distillation and reflux. I've definitely done it with some of my classes in AS, but it's quite, you know, how and when you teach things can vary from school to school. So yeah, I guess it depends when your school has done it. It's in the AS content, but whether you will have done it at AS if you do the full 2-year A-level is a different matter. Okay, so yeah, lovely. Thank you guys. So we're going to need to be a bit specific. Yeah, so there's some good use of terms going on here, guys. Specifically, if we're thinking scientifically, if we're thinking chemistry, we need to be talking about, we're separating an insoluble solid from a liquid or from a solvent. So yes, we are removing impurities in a way, but however, technically we might want to collect the solids. So you know, I guess that depends what you're calling the impurities in that case. But if we're being specific, we should probably say that the purpose is to separate insoluble solids from a solvent or liquid. Now I'm going to say solvent because I can't think of any time when you're using something that is not a solvent, apart from maybe at like Key Stage 3 when you're trying to separate like sand and water, in which case you're not trying to dissolve the water in the sand, but you know, you might be trying to dissolve water in sand. Good. So what are these? So we've got 2 types of filtration then. We've got gravity filtration, which is the one that hopefully you guys have all done at, there we go, you know, at Key Stage 3 even. And then there's this other one. What do we call this other one? What do we call this other filtration? Lovely. Thank you for all that information. That's great. Okay, yeah, so we've got a variety of different names for it. Vacuum filtration, you could call it suction filtration, or Buckner filtration, or filtration under reduced pressure. These are all valid names. So I'm going to call it vacuum it's being slow. Filtration. Lovely, good. Yeah, you'd use vacuum filtration. I mean, sometimes we even use it at GCSE, so hopefully you've already met it. But if you haven't, I love the Buckner Buckner flask, Buckner filtration. I think they're really useful. So can we do some naming of some equipment then? So you hopefully are recognizing all of this equipment. Let's start with the left-hand diagram. What can we call these bits of equipment? Good. Yeah, that's looking great. Lovely. Yeah, feel free to flick back, guys. If you're still worrying about exam boards and stuff, flick back to the beginning of the PowerPoint and just have a look at what is in the specification points. So I know that they're not that easy to recognize when you are not that used to looking at specifications. But for example, I can see that AQA, you have to distill a product from a reaction, which will probably involve, might involve some of these techniques, and that one and the tests for alcohols, aldehydes, alkenes, and carboxylic acids are all done in AS. But then there's also preparation of a pure organic solid, which is practical required activity number 10 for AQA, which is preparing a pure organic solid, testing its purity, or preparing a pure organic liquid. So they are required for the A level. So it just depends how much of it you're doing. And then in OCR, we've got, so OCR number 5 and 6 both use all of these, I think. Yep, use all of these things, and they're both AS practicals. Edexcel. I can't see. Where is it? Yeah, so Edexcel, you'd be using both of these filtering techniques. Separating funnel, yeah, you need to use in AS as well. So yeah, all of them. But if you flick back to our specification points, you can use that to help you. Okie dokie. Yes, lovely, good. Sorry, guys, you have been giving me all amazing information. So yes, I think it is a good idea to talk about the filter paper. Definitely, we need to talk about our conical flask. We can talk about our filter funnel. So it's the actual funnel that I'm pointing to there, and then inside is the filter paper. And something that we haven't got on here, but I think is always a good idea to mention is, and I've given myself something to label there are two things. There's the, actually I've probably labeled that in the wrong place, haven't I? Let's do the conical flask on the other side. So that's the conical flask. So what do we call the stuff that's left behind at the top, the solid, and the liquid that goes through? What do we call these? And we need to get them right because they like to refer to them in exam questions without telling you which is which. So what's the difference? Yeah, lovely. So you just need to remember which one's which. So just double check. So our residue is the thing that's left behind, and then the filtrate is the thing that goes through the filter paper. So that's great. Yeah, so residue, and that's how I remember it as well. The residue, it's a residue. It's been left behind. So the residue is the thing that's left behind, and then the filtrate must be the thing that's gone through the filter. But I always just remember the residue. And if you can remember the residue, you're all good. So really interesting question, actually, which is best? Everyone is different. As a teacher, having seen all three, they all have their pros and cons. I personally, unfortunately, did OCRB Salters, which is not one of the three main exam boards. And I myself did not enjoy the preparation that gave me for university. Lots of my peers did AQA and felt much more prepared for university than I did. However, OCRB Salters did do a lot of practical. So I did feel very practically prepared, which was good. So it does vary. It depends what kind of a learner you are, what you want to do with your chemistry. A-level Edexcel tends to go into a little bit more detail. They've got quite a lot of content in the AQA, in the Edexcel A-level specification. So they cover a lot more of the specification, a lot more content, I guess, than other exam boards do, which is a good thing in some ways, but also not a good thing in some ways. So yeah, they're all different. They all have their pros and cons, and they're all liked by different people for different reasons, I think. Would you suggest studying A-level content year 11 summer personally? Great question. I think what I would recommend doing is making sure you're solid. If you did triple GCSE, making sure you're solid on the triple content, but also making sure you're solid on GCSE content, because a lot of A-levels you will find so much harder if you aren't solid on your GCSE content. So things like moles, if you've done moles, making sure you're hot on structure of the atom, reactivities, electron configurations, things like that. I would recommend just not necessarily looking ahead to AS. If you want to, go for it. But if you're not sure, I would just make sure you're solid on your GCSE stuff, because it will set you in, if you're happy with it, it will set you in really good stead for doing your A-levels. Fabulous. Okay, right. Sorry, I got distracted by questions. So let's keep going, because otherwise I'm going to be behind time. So vacuum filtration then. So we can also call it Buckner or reduced pressure or other filtration. Give me some content, give me some equipment then, guys. What have we got here that we need to label? And let's give ourselves some other bits to label as well. So what can we label on here then, guys? Lovely, thank you, Laura. Nice to see you. So a Buckner flask. So that's that one. Our Buckner flask. What else have we got? Yeah, lovely. So I haven't even labeled that one as well. So well done, guys. Vacuum pump. We've got our filter paper. Filter paper, which needs to be present because our Buckner filter has holes in it, quite big holes. So if you just poured your solution, which lots of people do, into the flask without the filter paper there, it just goes straight through the holes, and there was no point in doing it. So that's good. Lovely. So we've got our vacuum pump. So we need something, and it totally depends on what your school or lab have, but your vacuum pump might be an actual vacuum pump, which is great, very useful, or it might be one that you connect to a sink, or it could be a hand pump one. It totally depends. And then we've got to have our Buckner filter, or Buckner funnel, actually I should say. Oops. As well. Is there anything I haven't labelled? Oh, and finally our residue and filtrate as well. We need to know the difference between them as well. Okay, so yes, you do, good point, Georgia. So that was going to link us in nicely, actually. So we are likely to use or want to use vacuum filtration for our recrystallization because it is one of the steps and it's very useful. Why do we? We might as well mention that now. Why do we need to, or why do we look to use vacuum filtration or filtration under reduced pressure when we're recrystallizing? We'll look at recrystallization in a second, but why do we need to do that? What's the point? Why can't we just filter it normally? What's useful about vacuum filtration? Is that, Vincent, is that from experience? Have you managed to lose your material? So in a way, you could talk about it becoming more pure. It's a good idea, but it's mainly because filtering under reduced pressure allows you to really remove all of the water from any water that might be trapped in and around the crystals. If you just do it via gravity filtration, and I say water, I actually mean any solvent, whichever solvent you're using, but it's most likely to be water. But if you do it under reduced pressure, you're really, really going to make sure you dry those crystals properly. Rather than just gravity filtration, which you will probably trap a fair amount of water in and amongst the crystals. So that's good. Yeah, exactly. It's to produce drier solids. It is quicker, Ash, actually. It definitely is quicker, which is another very good thing. But actually, the main point of it is that it dries our solid, removes all of that solvent properly. Hello, everybody. Hello, welcome. So let's keep going then. Final content slide is recrystallization. So what's the point of recrystallization? Why are we interested in recrystallizing stuff? Anybody want to have a think about what's the point of recrystallizing? If you're recrystallizing, you can hopefully tell that we've already got some crystals of something. So what's the point of recrystallizing? That's effort, isn't it? Well, surely we can just keep the crystals we've got. What's the point of recrystallizing? Yeah, good. Well done, Georgia. Exactly. Yeah, and Aisha as well. Exactly. We want to. It's a purification process. We're trying to make our crystals more pure. So the purpose of recrystallization is going to be to remove impurities, and in doing so, we might make bigger crystals potentially if that's what we're aiming to do. We might not, but the main purpose is to remove impurities to make our product more pure. And we're going to remove impurities from a solid using a solvent. So we have quite specific steps that you need to follow when you're talking about recrystallization. So it's a good idea to learn them. When you're recrystallizing, what are the first steps? What is the first thing we need to think about doing? We've got our solid crystals. How do we go about recrystallizing them? What are we going to do? What's the first step in purifying our products? Good, we need to dissolve them in a solvent. Now, that solvent, one of the key things that makes recrystallization A, so good, but B, so easy if you get it right, is what needs to happen to that solvent. What do we need to do with that solvent? We definitely need to add the solvent, but the solvent needs to be hot. This is where recrystallization, there's a skill to it. And it's why it's something that is very, yeah, well done, guys, exactly. It needs to be heated. Good. It's one of the things that we struggle with in the laboratory is getting recrystallization right, because our solvent has to be hot. So the first thing we need to do is to heat our solvent. Now, if you've got a flammable solvent, how are we going to heat our solvent? If our solvent's flammable, how are we going to heat it? Water bath, good. we're going to use a water bath, or if you've got a heating mantle, they're called as well, that's also fine. But we definitely obviously don't want to heat a flammable solvent using a Bunsen burner. But then if it's inflammable, then we can use our Bunsen. Whoops, flammable. Solvent, then we can use a Bunsen. Yeah, exactly. Lovely. Well done, guys. Fabulous. Okay, so now we've got a hot solvent. Then we are going to dissolve. And I think somebody said it earlier, it might have been Laura. We're going to dissolve our solid in the minimum amount of hot solvents. There's two key words there, and I'm going to highlight them to you. We need to dissolve our solid in the minimum amount of hot solvent. So we have to find, we have to have heated our solvent so that it will dissolve our solid. Why do we want it to be the minimum? Why does it need to be the minimum amount of hot solvent? What's the point of it being minimum? Yeah, brilliant. Well done, guys. So it's a saturated solution. Fantastic. Exactly right. We want it to be saturated. We want the moment some of that solvent it starts to cool down, or the moment some of that solvent starts to evaporate off, we want it to start recrystallizing again. It wants to be so saturated that the solution is so full of solid, and then there's only just the minimum amount of hot solvent needed, that as soon as it can start recrystallizing, it does. Exactly right. Well done, guys. So we want to make it a saturated solution. We want the minimum amount of our hot solvent. Once we've dissolved all of our solid in our beakers with the minimum amount of hot solvent, we can then leave it to cool. Oops, leave to cool, and at which point it will crystallize, hopefully pretty immediately, if we've done it properly. So our solvent can evaporate. Now, as it cools, well, one of the reasons that we need it to be a hot solvent, it needs to be soluble in a hot solvent, is because we also want, as it cools, we want our solution to crystallize as well. We want our solid, sorry, to crystallize. So this is why it's a really tricky but perfect process if you can get it right, because you have to have a solid that will dissolve, sorry, a solvent that will dissolve your solid when it's hot, but not preferably when it's cool. So it's quite difficult to find stuff, to find things that fit into that category that will dissolve something when it's hot, but not when it's cool, because that means as soon as you leave it to cool, some of the solvent can evaporate, but also as it cools down, your solid will recrystallize. Why does that need to be, why can't we just leave all of our solvent to evaporate off? Why do we have to have a solvent? Why does our solid have to recrystallize out while the solvent is still there? Why do we need our solid to be able to recrystallize while the solvent is still present? Anyone know? So we've got our evaporating dish, let's say, which has still got solvent in it, but has also got some lovely, I'm just going to do white crystals in it, but it's still got solvent present. Why does that need? Good, yeah, okay, fabulous. So our impurities need to stay in the solvent. If we just recrystallized, as in dissolved something and then let the solvent evaporate off again, we've not removed any impurities. Impurities are still there. But if our solid is soluble in a hot solvent but not in cold solvent, then when the cold solvent is there, our solid can crystallize, but the cold solvent will still contain the impurities. So our crystals will be pure and the impurities will stay in the solvent. Fabulous, exactly right. Lovely. So then we've got our crystals and some cold solvent. So we then need to filter. And then we can collect our crystals. So I think these are the key points for me, these two here, that it has to be a minimum amount so that it's saturated, and it has to be soluble when it is hot. And that is one of the reasons why I think chemistry is so cool, because it works so well. Okie dokie, fantastic. Right, how are we doing for time? Oh, a little bit behind. Okay, so I'm not going to go through this exam question, mainly because we're running out of time, but it is the same steps that we've just done on the previous slide to get the 4 marks. So 1, 2, 3, 4 for 4 marks. Okay, so apologies for that. We're not going to have time to go through the exam question. But that's because we like chatting and we've had some good questions going on, so never mind. You could be asked to rinse, but the only reason you would want to do that would be to get rid of any impurities that are just sat on the outside of the crystal. So that you could do that in the process of filtering, definitely. And in a laboratory setting, you would do that as well. You would definitely. In terms of the exam questions, you don't necessarily have to have said to rinse it, if that helps. Okay, so thank you so much for being here, guys. So hopefully you guys have gone through, recalled and applied your knowledge of separating funnels, recalled the different types of filtration we've got, and recalled our knowledge of recrystallization. Does anybody, so I don't know that we did, unless you've got a different mark scheme to me, Vincent. But as I think it was KKO said, yeah, in a laboratory setting, you would definitely rinse it to make sure you've got rid of all of your solvent impurities that are sat on the outside of your crystals. Definitely. Okay, thank you, Vincent. That's brilliant. Okay, that's not what I've got in my mark scheme, but that's good to know. Thank you. So before we go, just so that you guys have seen, I've got a couple of things that I'd love to show you. So we've got some upcoming web classes coming up. We've kind of booked in all of our July and August web classes. So please look on the YouTube schedule. But these are the web classes that we've got coming up. We've also got our tutoring on the website still. So we've got at least 4 classes a week. We cover the full curriculum. We have lots of amazing handouts, which, like you have seen from here, you can take home, you can use again, you can write on during the class, you can write on afterwards for revision, etc. So they're super useful. In the same way that on YouTube, we have all our previous recordings on the YouTube channel. On the website, we also have all of our past recordings on there. So if you miss a class or you want to go back and rewatch a class, then you can do that. That's all on there as well. And there's one-to-one support. So we are available to ask, you can ask as many questions as you like, and we try our best to answer as many of them as we can. So if you're interested in having a look at this, then please feel free to use our code, which is tutortrial7, all capitals, in the checkout. That gives you a 7-week, oh, that'd be lovely, 7-day free trial, 1 week of our tutoring. It expires in 24 hours. So if you want to use that code, then I would do so ASAP. And we've just popped it in our in the chat as well. And so is the schedules in the chat for you as well. So that is, I wanted to share that with you. The other thing I'd love to share with you super quickly as well is just to show you what we've got going on our website. So if I just flick over to, where's it gone? There we go. So if I show you the website here, we've got lots going on the website. We're just looking at the tutoring. So if I take you onto the tutoring page, that's what we were just talking about. I can show you that we have, let's scroll down. So if we go onto A-level chemistry and scroll down to the bottom. Oops. Keep going, scroll down to the bottom. So we've got a schedule here which shows all of our upcoming classes. So as you can see, we've got some sessions here that have been recorded. So here we go. So we had a Year 13 revision class on acids and bases last week. Then we also have, so we have web classes that happen, which are just like we've done in the YouTube class where we go through content, but we also have drop-in tutor sessions, and drop-in tutor sessions are ones that you guys can request to go through exam questions, topic, content, re-go over stuff from the web classes, whatever it is that you want, you request in advance, we schedule it in, and then you can turn up at drop-in tutor sessions and go through the stuff that you've requested. Or one of the amazing things I think, or the really useful things about this, is that it forces us to have spaced learning, which is proven to be one of the best ways to remember content and to learn things. So if you turn up to drop-in tutor sessions without having requested anything, somebody else has probably requested something that you find difficult, so you can go through that with them. So drop-in tutor sessions are really useful, but we also have web classes, so we go through the whole of the specification throughout the year so that you get the chance to cover everything with as much support as you want. The other thing that we can go through as well, and I'll just flick all the way back up to the top, that I wanted to show you is our resources. Now these are super exciting. That I wanted to show you guys is our revision cards. So we've got revision cards for AQA biology, OCR biology, AQA chemistry, OCR chemistry, let's scroll down, whoops, Edexcel maths and AQA physics. So we've got lots of these revision cards in the different exam boards. So they're tailored to the exam board and they're so useful. So if I go on to, let's go on to AQA chemistry. What they are is a really concise set of content for all of the specification points, for the whole specification for AQA or OCR, whichever exam board you've chosen. And on one side, if I just show you one side, we've got this content, which is the content that you need to know. And then on the back, you can see we have our exam questions. So there are exam questions with the marks and then a fully marked answer as well. So really good for revision, for learning content, sorry, and for testing your content. So super useful. So for example, if I show you the structure of the atom, this is the front of the card, looks like this. So it's the content that you need to know. And then the back, if I flick over to the back, has a couple of questions about the content to do with structure of the atom. And it shows you in the top right-hand corner as well, which spec points we're covering so that you can check it against the specification if you want, but you also know that we are covering all of the specification content. So they're so useful, and you can just have a quick flick through for some of those if you want. You can have a look at the information that we've given you, and you can see that we get exam questions that are linked in with that as well. So super useful. So if that's something you're interested in, please feel free to head over onto the website and have a look at those resources as well. So yes, great question. The cards are for both years, for AS and A2. So there will be a point at which the specification goes into the A2 content. So if you are just doing AS, you can get them now, just go through the AS content and then use the A2 content later. And I mean, super great price, I think, but very useful. So if you're the kind of person who likes having flashcards, small, concise, strong, well-worded content for your revision, and you want to be able to test yourself as well, then these are exactly the resource for you. So please feel free to go and have a look. Okay, right, I better head off because otherwise I'm going to overrun. But thank you so much for being here, guys. It's been amazing having you, and I hope to see you guys super soon because we've got another we'll have our next A-level chemistry coming up in about a month's time, so or maybe even less than that. So, but I will see you guys then. So have an amazing rest of your weekend, and I hope good luck to those of you who have got exams and results and stuff coming up soon, and I will see you guys very soon. Thank you very much. Well done, guys. Thank you, everybody. Have a lovely day. Well done. Thank you, guys.